Hello again, class. Welcome to week 7. This will be our last week for video lecture. We are going to cover chi-squared test and chi-square test for independence. Um, this is one of the most commonly used test statistics in biomedical sciences. There were a lot of you who actually submitted a paper critiquing um, the work of your colleagues in the medical field, and they have included chi-square statistics in their analytic plan. So let's discuss about let's discuss chi-squared statistics in detail, and I will try to attempt as well to simultaneously discuss chi-square test for independence because they are very closely related. The concept is similar, and I will demonstrate to you basically that when you do a chi-square test for independence, you are using the chi-square test. So let's begin. So let's start with the basic question of what is chi-square test? Well, chi-square test is a test statistics that was developed by Carl Pearson, and you're probably familiar with him because he's also the statistician who developed the Pearson's correlation. But let's start with the Pearson's chi-square right now. This is a test that's developed by Carl Pearson to compare whether the variation in the data is due to chance or is it really due to the variable. For example, if you are interested in knowing whether the gender variable in your study on, for example, let's think about the other categorical variable of a study, for example, um, groupings of um, the two groupings for one specifically one arm that received placebo and the other arm that received the experimental drug. So you have two categorical variables and you are trying to determine whether the the difference between the two arms, which is your placebo versus your experimental drug arm, is actually due whether the variation between those two values of the two arms is due to chance or is it due to the variable of your interest that's also categorical, such as your gender, whether it's because either a male or a female gender that you are interested in testing. So the next question then is, what is chi-square test for independence? How is this related to chi-squared test? Well, the chi-square test for independence is a test statistics to determine whether there is a significant relationship between two categorical variables using the chi-square test. So to illustrate this, I actually have prepared an example. It's hard to sort of like separate these two because they are so conceptually related, and it's a lot easier to discuss chi-squared tests and chi-square test for independence simultaneously, as long as you will follow the discussion very closely. So again, back to what is chi-squared. So what's the formula then when we talk about chi-squared test? Well, chi-squared is represented by x squared, is the sum of the square of the observed values minus the expected values, and then divided by the expected values. So again, the chi-squared test statistics is represented by your x squared, and then the Greek symbol there stands for the sum of, and then O stands for observed frequencies, and E is for the expected frequencies. And because the formula says you have to sum this, so you actually need to perform the square root first of the square of the observed values minus the expected values, and then divided by the expected values or expected frequencies. So how about now when we talk about chi-square test statistics for independence? How does the formula looks like? Well, it uses the chi-square test formula, same expression. It's x2 for chi-square, and it follows the logic of the mathematical calculation, that is the sum of the square root of the observed, as you can see it's letter O, minus the expected values. But now you are seeing small r and a small c next to the observed and next to the expected frequencies or values. Well, R is the number of levels of one categorical variable, and C is the number of levels of the other categorical variable. Because now you're talking about independence, which means you have two samples with two categorical variables. So you just simply need to add the levels of the categorical variable from one sample, and then also multiply it with the number of levels for the other categorical variable. And so the description of chi-square test statistics for independence goes like this. It will be x squared equals the sum of the observed frequencies that is using the number of levels of one categorical variables multiplied by the number of levels of the other categorical variables, and then you subtract it with the expected frequencies, again using the number of levels for one categorical variable multiplied by the number of levels for the other categorical variable. You square that, and then you divided it by the expected frequency in a similar fashion that you're also going to consider the number of levels for one categorical variable, represented by R, and also the number of levels for the other categorical variable, represented by letter C. So let's put this into action. So in a chi-squared test, The null hypothesis simply says that there is no significant difference between the observed and the expected frequencies. Remember, the simple formula was just the sum of the square of the observed minus the expected frequencies divided by the expected frequencies. That's the basic formula for chi-squared test. So the null hypothesis for chi-squared test is also very simple. You just say there is no significant difference between the observed and expected frequencies. And in a chi-squared test, typically you just need two outcome in order to create this null hypothesis. I mean, when you do an experiment, there has to be at least two outcomes, because if you only have one, then you're actually not experimenting. You're not comparing anything with anything. So that's why in chi-squared tests, there has to be two outcomes, and then your null hypothesis would be there's no significant difference between the observed and the expected frequency, or otherwise you can also call this outcome. What is your observed outcome and what is your expected outcome? And your null hypothesis would be there's no significant difference between the observed and the expected frequencies or outcomes. So I have prepared here an actual data that I'm going to present next month in Rome for the International Myeloma Conference. This is actually the data that my research team from the International Myeloma Foundation Nurse Leadership Board gathered through an online survey of multiple myeloma patients who have at least received chemotherapy already. So these are multiple myeloma survivors. And we sent them the questionnaire from one of the government validated and reliable questionnaires on preventive and health maintenance patterns um, among healthy individuals. The reason why we sent this survey to uh, multiple myeloma patients who are cancer patients, that in the past decade there was at least five new drugs that have been approved by the FDA uh, for the treatment of multiple myeloma, and these five approvals actually resulted to a significant improvement of the overall survival of multiple myeloma patients. And because they have at least 60% of the patients will already make it to the fifth year, and about 25% will make it to the 10th year, then it is important then that these patients need to do health maintenance and preventive practices because their survival has already improved and they might get preventable diseases which they are not actually monitoring anymore because they thought they're going to die very soon with cancer. So that's the background of this study. So we sent this online survey to the list-serve member of the International Myeloma Foundation. And the questionnaire had a total of about 20 items. And these are all about their health maintenance practices, preventive practices, just like do you see your physician at least, or do you see your primary care physician at least once a year, for example, for their cholesterol checkup, for um, um, what else do you do for when you go to your physician annually? Your cholesterol, some situations you might also get your thyroid. So For every answer of yes that they have performed their health maintenance or preventive practices, of course, for women, it's their mammography. For men, it's their prostate. So there were um, gender specific questions. But the bottom line is that the questionnaire will give a perfect score of 20 if they are totally on it in performing all of their health maintenance and preventive services that's recommended by the US Human Health and Services. So what we did then was that because the score was perfect was 20, we created categories, and that's the categories of the adequacy of health maintenance. And it was very easy to create categories or categorical variable for the adequacy of health maintenance because the perfect score was 20. So we just divided it into quartiles. So we have, you know, those who have scored obviously 5 out of the 20 will belong to the first quartile. That's the zero point zero 0.00 to 0.20. That's the 20. That's the first quartile. And then the second quartile is the one that has a score of 0.21 to zero point 0.4. And then, of course, those who are really super, super compliant are the one that had scored, you know, 18 out of the 20. And so they belong to 0.81 to 1.0. So they belong to the top quartile. So that's how we got the that's what you call compute. It's a function on SPSS where you can compute and then create different categorical variables, but you have to specify the values of those categorical variables, and the computer will just do it for you. So it's very easy. So we did that, and what we found was that we were interested whether among men who were partnered or non-partnered, so the number one is coded as P as partnered, number two is coded as non-partnered. We wanted to know whether there was, remember in chi-square test of independence, because this is now looking at categorical variables. And so I have two categorical variables in my depend, at least minimum of two categorical variables in my dependent variable, which is the adequacy of health maintenance, and then my independent variable, which is the partner status for men. So if you look at the data, what we have is that for the partnered men, 7 actually belong to the first quartile, and then for the non-partnered, 5 subject belong to that. And then in the second quartile, 12 partnered belong to that group, and 5 non-partnered men belong to the second quartile, and so on and so forth. And as you can see on this table here, you will get the total on the farther right. So if you have 7 partnered in the first quartile and 5 non-partnered in the first quartile, the total for the first quartile then is 12. And you do that for the next quartile all the way to the top quartile, and then you also get a total for how many respondents do you have for the partnered, and then how many respondents you have for the non-partnered, total in all of the different categorical quartiles. And the reason why I emphasize this is that remember that the formula for chi-square statistics is that observe minus expected frequency, and you square that, and then you divided it by the expected frequencies. Well, in this situation, then we need to look at how would an expected frequency under the null hypothesis would look like, because this is now the data that we gathered from our survey. These are now actual values that we got from the patient. So how does the expected frequency under the null hypothesis using the chi-squared test would look like? I'd like you to ignore the bottom part because we're going to look at that later, the Pearson's chi-square, and then you have 4 in close and open parentheses, which is the degree of freedom, because I'm gonna talk about that in a little bit, and then the chi-square test statistic value, and then the p-value. I don't want you to look at that yet. Just look at what we got from the survey, and that is the observed frequency. That is the number that you're going to plug in into the formula of chi-squared tests. So how are we going to get the expected frequencies under the null hypothesis? Well, it's very simple. We retain the total. So our total will, on the different quartile is 12, 17, 42, 27, and 10. As you can see, I'm going to flip back here. So you can see there the total 12, 17, 42, 27, and 10. So when you look at then in terms of the expected frequencies for the null hypothesis, you simply just have to copy the total frequencies and your expected frequencies when there's null, because the null hypothesis, there is no difference in the observed and expected frequency. That is the statement in the null hypothesis for chi-squared test. So basically, you just divide the total. So for the first quartile, if you have a total of 12, then the partner would be 6. The non-partner would be also 6, total 12. And then on the second quartile, right here, if the total is 17, then you divide it by 2, then 8.5 will be for the partnered, and then 8.5 for the non-partnered, and same thing that you do for the next quartile. The total was 41. You divide it simply by 2, because that is again an expression of what they say as that there's no difference in the observed and the expected frequencies. So you'll have equal number then of frequencies in partnered and non-partnered in all the different categories of the adequacy of health maintenance. So you can see there's 6 and 6, 8.5 and 8.5, 21 and 21, 13.5 and 13.5, 5 and 5, and you still get the same total of 108. So remember the total here for my observed frequency is 108. You also have 108 total for the expected frequencies. Moving on. So I just explained to you the chi-squared test. What about now the null and the alternative hypothesis in chi-squared test for independence? Well, in our example, our null hypothesis can simply be said that our variable A, which is the adequacy of health maintenance, and variable B, partner status among men, are independent, because now we're saying that we are using the chi-squared test for independence, to check for independence. So our alternative hypothesis will be stated as the adequacy of health maintenance and partner status are not independent. So, how do we apply then some of the important concepts that we've learned from chi-squared statistics into chi-square test statistics for independence? Well, let's go back to the degrees of freedom. Well, in an experiment, as I've mentioned earlier, there's at least two outcomes. So for chi-square test statistics, the degree of freedom is equal to df equals n minus 1, where n is the number of outcomes. Remember, when you do an experiment, there's always two outcomes at a minimum, and the degrees of freedom for chi-square test statistics is just simply n minus 1, where n is the number of outcomes. So if you're doing, if you compare basically um, two arms and you have two outcomes, then your degrees of freedom would be 1. Now for chi-square test for independence, the degrees of freedom you're going to apply now the additional concepts of the number of levels of the first categorical variable for your dependent, and then also the number of levels of the categorical variable for your independent variable. So, and those are represented by your letter R and your letter C. And to calculate then for the degrees of freedom for the chi-square test for independence, the degrees of freedom is simply multiplying the difference of your number of levels of your categorical variables minus 1 with, so it's multiplication, so you obtain the difference of the first, the number of levels of the categorical variable, and then you multiply that with the difference of the number of levels of the other categorical variable minus 1. So in our example, let me go back again. Remember that our adequacy of health maintenance, we have um, 5 quartiles. So we count, it's basically 1, 2, 3, 4, 5. So we have 5 levels in this categorical variable, and so applying that to our the formula for chi-square test for independence and calculating the degrees of freedom, then you have 5 minus 1. And so what's the difference? That would be 4. And then the formula says you multiply that with the difference of the number of levels of the other categorical variable minus 1. Well, the other categorical variable only had 2 levels, because remember we were looking at the partner versus the non-partner. So we only have 2 levels in that categorical variable, and so that's 2 minus 1. So the difference between 5 and 1 is 4. You multiply that by the difference 2 minus 1. That is 4 times 1. So the degrees of freedom in our example is 4. What about critical values? Well, critical values, I think we keep talking about this for almost every test statistics. These are the observed values in test statistics that are extreme, and it indicates that the probabilities that these values are due to chance are being rejected using the null hypothesis. We also know that the higher the critical values, the more it becomes extreme, and the more it is statistically significant. And you will see your p-value just getting lots of zeros as you get your critical values higher and higher, and your observed values becoming more extreme. So now let's go back to our example where we got our Pearson chi-square um, test statistics value with a degrees of freedom of 4. It was 12.0482. Now I wrote here that this is higher than the critical value of 7.84 at the 0.05 significance level, which is always the standard. We always set our significance level at 0.05. Now you might wonder then, where did I get the critical value of 7.84 at 0.05 significance level? Well, you need to go back to what we call the chi-square distribution. So just like your t-test, there's a distribution, there's critical values, and they have specific significance level based on those critical values. So that's the next slide is the p-value then. So the p-value is the probability of observing a sample statistics as extreme as the test statistics using the chi-square distribution. How do we do this? Well, we need to simultaneously use the degrees of freedom that we computed earlier, and our answer of course was 4. We had a degrees of freedom of 4. So simply put, when we set our p-value at 0.05, we mean that we are about 95% sure that we are going to accept or reject the null hypothesis. Now, in our example, our p-value with our chi-square statistics of 12.0482, we get a critical value of 7.84 at 0.05 significance. Now, in our example, our p-value was 0.017, and I'm going to show that to you again right here. That in this slide at the bottom, as you can see, our Pearson chi-square statistics with a degree of freedom of 4, our critical value was 12.0482 and our p-value was 0.017. Well, that's because 12.0482 is definitely higher than the 7.84 at a p-value of 0.05. So the higher the higher your Pearson's chi-square, the higher it is than the critical value set at the 0.05, then your p-value will also be very high, because now remember the p-values simply state that you are 95% sure that you're going to reject or accept the null hypothesis. Well, in this case, our p-value is higher than the 0.05, so we're going to reject the null hypothesis. I mean, I'm this is 0.017, so this is definitely lower than the 0.05 significance level, so we're going to reject the null hypothesis. If we get higher than the 0.05 significance level p-value, then we are going to accept the null hypothesis. So right here then, how are we going to interpret our results? Well, again, here is the chi-square distribution, and I want to point out to you that our degrees of freedom is 4. And we said that our p-value, our significance level, has to be a minimum of 0.05. So you just look at degrees of freedom of 4 at the 0.05 significance level. That's your p-value. What we need is 9.49 for the chi-square statistics, for our computed chi-square statistics to achieve a 0.05 significance. Well, our computed chi-square test statistics for our sample was actually 12. So right here was around, we said it was 0.01. We achieve a 0.01 p-value with our sample, and so a degree of freedom, that's roughly about 13.28. So that's how this table works, the chi-square distribution table. So I think what I'd like to just simply say here is that if you set your significance level at 0.05, and you only have, if you have a degree of freedom of 1 because you only have 2 outcomes, so n minus 1, 2 minus 1 would be 1, and at a 0.05, your chi-square test statistic value is 3.84. Anything, anything above 3.84 when you only have 2 outcomes will give you a statistically significant difference between those between the variables that you are testing. So 3.84, as you can see here, anything above 3.84, the statistical significance just get higher and higher, and you'll see more and more zeros. So that's the chi-square distribution table. So to do a formal interpretation of the results, again, the rule is very simple. You need to compare the chi-square p-value to the significance level, and then reject the null hypothesis when the p-value is less than the significance level of 0.05. In our example, the p-value was 0.01, which or 0.017, which is clearly less than the significance level of 0.05. Therefore, we cannot accept the null hypothesis. We have to reject the null hypothesis. And then we conclude that there is a relationship between adequacy of health maintenance and partner status among men. So how would we create a conclusion once we have this? Then our conclusion should be related to our results, and as researchers, then we should say in our conclusion that among men, partner status has a significant relationship with the adequacy of health maintenance. So if you are a clinician, then you would want to know, is it the partnered or is it the non-partnered that have adequate or inadequate health maintenance? So if we go back again to our data set, it looks like we have so many partnered right here status that actually one more we have so many, because that was the null hypothesis. So we have so many partnered status men who are actually in uh, third, the fourth, and the fifth quartile. So the top quartile, you see more partnered men there. So basically, what that tells you then, that partnered men have better adequacy of health maintenance. So obviously they have higher global score, because remember, we put the global score of 20 into five quartiles, and the 1.0 are the one who are scoring 20 or perfect score for their adequacy of health maintenance. So that is a illustration of chi-squared test being used in a chi-square test statistics for independence. All right, so I hope that you have learned chi-square statistics. Again, remember, they have to be categorical variables if you're going to do chi-square test for independence. Categorical variables are definitely not ratio data or interval data, because you are going to violate the rules of chi-square test for independence. The rule clearly says that this is applicable to categorical variables only. So you must use other test statistics if your variables are not categorical variables. Okay? All right, so that's chi-square test applied to chi-square test for independence. If you have any question, please feel free to request for FaceTime if your question is long, or if you need to talk to me, you can always Viber me. And then again, if your question is short and just simple clarification, you can always email me. And that's the end of this video lecture on chi-square test and chi-square test for independence.